That's okay. Okay, let me start. So today we are going to discuss a new topic, non-uniformity in cellular automata. What we have discussed till now, starting from the definition, basic definition of cellular automata, and then we covered the set theoretic properties, Gardner-Biden theorem, reversibility, etc. In all the cases, we have considered the classical definition of cellular automata. In this class, we shall try to deviate from the classical definition, and we shall tell what are the reasons of the definition, why we want to do so. So, that will be covered in this class. So non-uniformity. So before going to that, let us recall the definition of cellular automata. Cellular automaton is a quadruple, right? It's a quadruple, and it has this 4 L, S, M, R. Okay, so L, where L is the lattice, d-dimensional lattice, L subset of z to the power d. You may recall that when we first defined the cellular automata, we have directly written z to the power d. Okay, here we are writing here L subset of z to the power d, means sometimes it can be equal to z to the power d, sometimes as a subset of z to the power d, because while we have introduced finite cellular automata, in that case L, the finite one, the first subset of z to the power d. So to cover all these things, we have we have written in this way: L is subset of z to the power d. So it's a lattice. The second component of that quadruple is S, is a finite set of states, right? And then M is a neighborhood vector. Recall that what is M? V1, V2, Vm. They're the neighbors. Okay, they're actually the cells of that lattice, right? Each V actually should be Vi, in fact. Each V1, V2, Vm. So they're actually the cells of my lattice, and the cell under consideration as a V. So that V depends on this M number of M neighbors. So we call M, capital M, is a neighborhood vector, and R is S to the power M to S is a transition function. This is actually a finite automaton, which is transition function. We call it local rule. So we have defined this one. Okay. So this quadruple having 4 components, L, S, M, and R. We have discussed that cellular automata is a discrete system. Here time and space both are discrete, and it evolves from one step to another step, then another step. In this way it evolves. We have seen that evolution in case of game of life, in case of ECA rules. We have seen, from one initial configuration, it moves to another configuration, and so on. So here, space is discrete, obviously. So L is, z to the power d, it says the space is discrete. Time is also discrete. So it's a dynamical system. Okay, it moves from one configuration to another configuration, then another configuration, and so on. And actually, there, the CA performs a local computation. That R is the local rule. So we call the elements of L right? We call the elements of lattice as cell. So each cell computes, and the computation is performed by the function or by the local rule called R, right? So R is the local rule here. So R performs the computation, local computation, and out of that computation, we get a global computation. Okay. Anyway, these things are covered. So now, sometime we identify three properties of a cellular automaton. These are locality, synchronicity, and uniformity. So three basic properties of our automaton: locality, right, synchronicity, and uniformity. What is the locality? See here, it's a computation of R. Computation by means of R is local computation. What I've said, C as a whole compute, right? But actually, the cells compute, right? The individual cells, they compute. And for that computation, they use R, right? The local rule R is used. So, and the R, how it computes? It looks at the states of its neighbors, right? What is happening outside of that? What is happening over the whole lattice? A cell does know. In fact, a cell does not want to know. It collects information of its neighbors and based on that computes. That's the locality. And what is the meaning of synchronicity? Synchronicity means all the cells which are performing the local computation, they're updated simultaneously. This synchronous system is the meaning of synchronicity, right? And then what is the meaning of uniformity? That all the cells, they use the same local rule. So see, actual computation is performed by this R, and that R is unique over the lattice. Means all the cells use that particular R. That is called the uniformity. The rules are uniform. So three properties: locality, synchronicity, and uniformity. Right? So we identify our cellular automaton by these three properties. Right? Okay. So although there are these three properties, sometimes we identify that, cellular automaton, its classical definition of automaton, in that definition, uniformity is everywhere. Everything is uniform. Okay. Everything is uniform. Right. How it's good? Okay, let me go back to the Jamboard and let me tell you. Just a minute. Okay. See what I'm saying here. Say these three properties. What does it mean actually? See here, I'm saying there the one dimensional. Sorry. Consider one-dimensional here. So in this case, all the most of the example I'll give. So one-dimensional. Suppose, so this is my cell. Suppose this is my cell I. This is my cell I minus 1. This is my cell I plus 1, and so on. Okay. Then it is I plus 2, I plus 3, I plus 4, etc. this way. So suppose I'm considering this particular cell. Now, see what is the meaning of this locality. Say I am applying rule R here. I am applying rule R here. And suppose for simplicity you consider that this rule depends on these three cells. Okay. Now see what is happening when R computes. What are what this cell says? It says its neighbor state, right? Based on that, R finds its next state. It goes to the next one. Now what is happening here? For example, here, that is, I mean, R doesn't know this one, right? So this is called locality. And what is the uniformity? See, this I cell is using R. See, that distant cell is also using R. See, this cell is also using R, right? And here also, when this R is, when we're talking about this R, then it takes this, this, then it considers the state of these three cells, right? So then these three cells, these are considered. So this is the meaning of uniformity. Everywhere the same rule is used. And what is the meaning of synchronicity? See, all the cells are updated simultaneously. Okay. So for example, if a configuration is like this 0 0 0 1 1 0 0 1 0 0, etc., 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 then each cell, so then when you find a configuration, what do you do? For example, so next configuration is 1 1 0 1 1, etc., etc. Then how we can find it out? See, all the cells, all the states, are updated. So actually here, what you see here, all the cells are updated simultaneously. So these three property: locality, synchronicity, and uniformity. So in a cellular automaton, be it one-dimensional, be it two-dimensional, be it n-dimensional, is identified by these three properties. Now here we argue two things. First one is uniformity. See, although I am seeing all are using the same rules and we are saying it's uniformity, but see, apart from that uniformity, you can find uniformity everywhere. See here, look at this neighbor connection, this particular cell. This cell, okay, let me use the different color. This cell, say this cell, this particular cell, it depends on its left neighbor, its right neighbor. Same is here. This cell also depends on left neighbor, right neighbor. In fact, when I specify what is my R, I write R as in this way, say to the power m to s, right? So when I specify m, actually I am specifying on which neighbors a cell depend on. So therefore, in the neighborhood dependency, in a cellular automaton, there is uniformity, right? So there are uniformities everywhere in a cellular automaton, right? So let me identify those uniformity. Let me identify those uniformity. So a cellular automaton is uniform in all respects. Uniformity comes in three ways in a cellular automaton. Just let us identify. Say uniform neighborhood interaction, which I just now said. Here, each cell depends on a similar type of neighbors. In the example, if it is thin about CA, right? In the example which I have given just now, here, a cell, each cell depends on its left neighbor and as well as right neighbor and self, right? So Neighborhood dependency, that is uniform, right? Uniform update. All the cells are updated uniformly. That is synchronicity, right? Synchronicity means what we are saying here, that all the cells are updated simultaneously. So there's uniformity. So uniform update. Okay. And finally, the name is uniformity. That's the uniform rule. Okay. So all the cells follow same nested function. Right. So I want to argue that classical cellular automata are uniform in all respect, right? And these aspects we can identify three ways. They are neighborhood interconnection is uniform, update is uniform, rule is uniform. Okay, in literature, we classify, we identify three basic properties of an automaton, of a cellular automaton: locality, synchronicity, uniformity. But synchronicity is one kind of uniformity. Right? It's all the cells update, simultaneously. Okay, uniformity. Apart from that, synchronicity is also uniformity, right? And when I'm declaring, when I'm specifying a rule, a particular uniform rule, that also unifying the neighborhood dependency. So we can identify, these three basic uniformity in a classical cellular automata. Note that in all the cases, we have not touched the property of locality. In my whole discussion, locality issue will not be touched, right? And now here I want to relax this uniformity constraint. As I've said, I want to disobey some properties of classical cellular automata. These properties are informative properties, but we shall respect always locality issue of a cellular automata. Right. Now, as I've said, that we want to deviate from the classical definition, and how to deviate? We want to introduce non-uniformity in cellular automata structure. Right here, what I get here, three kinds of uniformity I have received. Right, uniform neighborhood interaction. Right, that I've said, uniform neighborhood interaction. I can relax the uniformity constraint. Uniform update constraint, I can relax that one. Uniform rule, I can relax that constraint. After relaxing these constraint, I get three kind of automation, or three kinds of cell automation. First one is very general one, which we call automata-network, where the first uniformity constraint is disobeyed. Right, uniform neighborhood interaction, that condition, constraint is disobeyed here. Right, so there is each cell depends on similar type of neighbors. That may not be. That may vary from cell to cell. Second is uniform update. Here, each cell is updated simultaneously. Right, the simultaneous action is there. That is also disobeyed. When it is disobeyed, then we get asynchronous cellular automata. And finally, if we disobey the uniform rule, okay, all the cells are forced to follow the same nested value, nested function. If there is disobeyed, then we get hybrid cellular automata. Sometimes we call them non-uniform cellular automata. So in this way, we are introducing non-uniformity of in cellular automata, in classical cellular automata. So all these cellular automata, they are not classical, they are non-classical cellular automata, right? Because we have compromised some properties of cellular automata. Why we are compromising so that clear, as I've said before. Okay. As I've said, let me repeat it again. Here, we shall not compromise with the locality issue, right? So let me briefly talk about automata network. See, in case of automata network, see here one more thing, one more information you can find in a classical definition of CA. That is the lattice. Lattice also very regular, right? And it's uniform, right? So you can see a grids, grid view, grid-like view. You can get a grid that is very uniform. The structure is uniform. We call it regular network. Regular input is there. Automata network, first these honors that one. It defined over irregular network. And by doing so, a cell may depend on arbitrary number of neighbors. Okay. So some works have been done in early 80s and then in 80s, 90s. And also it has a new name called graph cell automata. Means, you define a graph and place the final automation in the node of the graph. Okay, and the graph will tell you, the node structure of individual node. Okay, just like that one. So let me. So if I come back to this jam, what is that mean? So suppose that I'm defining graph. Say this kind of graph, if I define, arbitrary graph I'm drawing. So now, sorry. Suppose I am saying this kind of thing. It's a graph, right? So I'm defining arbitrary graph. Now what I'm doing here, so this line is saying the neighborhood dependency. For example, consider this one. So this is the neighbor of this one, this four neighbors. In this case, for this one, it has 3 neighbors, right? So it's the irregular network. The network is the irregular. So what I'm doing here, I am placing an final automaton, in this, in these nodes. And property of the final automaton is it can deal with different number of neighbors, right? So here the network becomes non-uniform. Although automata network, graph cell automata, they're not same. So 2 names are used in literature, but they're of same type. Neighbor interconnection, neighbor dependency, that property is relaxed here. Your network is not regular. Sometime here there's a problem, may say, sometime here. So for example, if you're considering it's arbitrary graph here, you can see here, so you may argue that, say for example, for this particular node, okay, let me use different color. Let me, sorry. So if I use different color, say, so for this particular node, okay, one may argue that this node is not the local neighbor, right? Since you are considering arbitrary node, arbitrary graph, and a node may depend on arbitrary number of nodes. Sometimes a node may depend on some distant node. To some extent, it's distant node. So you can get some kind of non-local interaction, non-local computation. Okay, that you may argue here, but it gives some kind of flexibility. It gives you the flavor that the computation can be local as well as non-local. However, in case of cellular automata, we particularly want to concentrate on local interaction. Okay. Anyway, this is about automata network. Okay. This has some applications. For that, actually, it was developed. So it violates that one, that uniform neighborhood dependency. That property is violated. Also, it violates the uniform grid structure, lattice structure. So there is the uniform lattice. The network is the uniform. Is an irregular network. Okay. Okay. So we don't want to discuss more about automata network. So next we are moving to the next class of non-classical cellular automata called asynchronous cellular automata. See, what are the properties here? See, in case of classical cellular automata, sometimes we call it synchronous cellular automata. See, all the cells are updated simultaneously. How you can do it? How can you ensure that all the cells will be updated uniformly? We have some idea about digital logic, and we always do it. How can we do it? You always do it by introducing a clock, a global clock, right? A clock actually ensures that all the nodes, all the cells, all the circuits update simultaneously. Here, in case of classical cellular automata, I'm saying it's synchronous. All are updated simultaneously. How is possible? It's possible only if I introduce a global clock, right? A global clock is there, and when clock comes, all the cells are updated. See, in case of cellular automata, I am getting a view of parallelism. Cells are running parallelly, and there's a view of independence. Cells are running, locally and independently. But there's a problem. The cells are forced to get updated simultaneously. in asynchronous cellular automata, as I've said, we want to relax that constraint, synchronicity constraint, uniform update constraint. So here, what you're doing, we're allowing the independent update of cellular automata, of the cells of the cellular automata, right? So here, we are making the cells independent. By saying this word, I actually claiming that although classical cellular automata, there are several apparently independent cells, but actually they are not independent because they are forced to get updated simultaneously. There's a clock pulse. Based on the arrival of clock pulse, they are forced to get updated. We want to relax this one, right? We want to get a self-timed cell. What is the meaning of update? Cell update means an action taken by a cell. And what is the meaning of independence? I'm saying you act whenever you want to act. And if you don't act, if you don't want to act, do not act. You remain silent. So that kind of independence we want to allow. Why you are doing so? So at this stage, I can give some intuitive reasoning. And what is its need? See, cellular automata from the from when it was developed, it was used to model the physical systems, natural systems. And as I have said, cellular automata was invented by wanted to model self-reproduction, right? Very natural phenomena. So cellular automata always targeted to model natural systems. But in nature, you don't always find any global clock, right? You don't always find that someone is dictating when to get updated, when not. Rather, in many cases, you find the independence of the components. So if you look at a forest, for example, right? In the forest, there are several trees. They grow. Okay, the trees, they're independent to some extent. They have collaboration. On the other hand, the trees are having independence. No tree is saying, in general, that you must grow now, you stop working now, or you do act now. So there are many examples where you find, this kind of independence, right? So if we want to make cellular automata more powerful in that sense, that it will be able to model the nature in a better way, then we should give this independence, right? So this is the motivation of developing asynchronous cellular automata. Some authors have called it self-timed automata. That means ultimately cellular automata, they are they are synthetic system, right? So to act, you need a timer. So the proposal is, okay, each cell has its own timer, right? So self-timed automata. Some authors have called it self-timed automata. And from asynchronous cellular automata, some develop progressive cellular automata. So first, the idea is same. Idea is we want to allow independent acting of cells, right? And motivation is we want to develop better model of computation so that it can model the natural phenomenon in a better way. Okay, there's a motivation. Now, question is, how can we, implement the independence? What I've said now. So we want to model independence is good, but how? Ultimately, to develop, ultimately you have to run the automata in a computer. Okay, so what is the model of implementing this independence? Right. In one word, I can say that cells act when they want to act. But if I ask you, develop a C and run it in a computer, how will model it? How can model it? So modeling of independence is really difficult. We don't know how to model. There is no fixed way. That is the only way. But almost accepted model, accepted way of modeling this independence is this one. Some probability. Okay, you use probability. Using a probability does not ensure you that cells are independent. But if you think that I am assigning a probability to a cell and then I am running that automata in my computer, then as if I am modeling independence, because the cells are not always updated. Okay, so this is the accepted way of modeling independence. Okay, that you probabilistically, update the cells. Now, question is, how I apply the probability? There are several ways of update schemes, but two popular schemes are there. There are two popular schemes that we'll discuss here. That is called fully asynchronous update. There is alpha-asynchronous update. And fully asynchronous update means a cell is chosen uniformly randomly at each time step to update. So you have a set of cells. Okay, if it is 1D, so an array of cells. If it is 2D, a grid of cells. If you are applying fully asynchronous updating scheme, it means you choose one cell uniformly at random for update at each time step. Okay, so each time step, time is there. At each time step, I'm choosing one cell uniformly at random, and then that cell is updated, and the rest cells are not updated. And next time step again, from the whole set of cells, another cell is chosen uniformly at random, right? And then that cell is updated. This is fully asynchronous update. So it may appear to you that it's correct that as if the cells are updated serially, one by one. So one cell at a time. That's correct. But which cell is to be updated? That is, decided randomly, uniformly and randomly. Right. That's the important thing. Anyway, an alpha-asynchronous update is in this model, each cell is updated with probability alpha. It implies obviously that a cell is not updated with probability 1 minus alpha. Now, that if alpha equal to 1, if alpha is equal to 1, means if one asynchronous update, if alpha equal to 1, then the system, the CA, becomes asynchronous because all the cells are updated. Each cell is updated with probability 1. So alpha-asynchronous update, you can say, is generalization of classical synchronous shape, classical shape, right? And here, as alpha, you can put 0.9, 0.5, 0.001, etc. Right? And if you put 0, the trivial one, it will update. So these two popular models have been used to study asynchronous cellular automata. Somebody has argued that fully asynchronous update, they are the most natural one. So I shall not go to that argument. And there are many other updating schemes. Okay, some updating schemes are also derived from these basic updating schemes. Some are different, such as beta updating scheme that I'm not discussing here. So two popular updating schemes, most of the literature you find in they consider one of these two updating schemes, right? And what you'll find that in most of the cases, almost all cases rather, finite cellular automata are considered. Okay, although in the definition there is no mention of finiteness, CH, maybe infinite CH, but the word you find, they consider, the CA, cellular automata, as finite, right? This is assumed. So generally, finiteness is considered here. Okay, and I shall give an example how it works, how it differs. Okay, I shall go to in detail this updating scheme, and in that detail we shall consider finite cellular automata only, right? Okay, but recall that we have considered, we have covered finite cellular automata before, and in case of finite cellular automata there is a case of boundary condition. So let me briefly look at the boundary conditions of a cellular automata for a finite cellular automaton. Then we shall come back to this topic again. So boundary conditions, we have boundary conditions for finite CAs only, because in case of if set is infinite, there is no question of boundary. There are two popular boundary conditions. One is called open boundary condition, and it's called periodic boundary condition. Okay, I have given a few examples. So so in open boundary condition means, in the right hand side I give one example of this here. In open boundary condition, what does it mean? It means that it open terms in the boundaries. After boundary there is no other cell, right? And in that case, so and it is assumed the boundary cells, other cells, they assume that the missing neighbors, some neighbors are missing here, the missing neighbors are in some particular state. Okay, that state may be fixed, may change, but the cells which are missing, as if they are always in the particular state, right? That is assumed. It's called in case of open boundary condition. On the other hand, in case of periodic boundary condition, the lattice is spatially periodic, right? You see in one boundary case here, you can see here that in case of periodic boundary condition, as if the cells, they form a circular array. right? The cells form a circular circular array. So therefore, in case of n cell CA, right? After cell n minus 1, the next cell is the first cell. After the last cell, what I get, the next cell is the first cell, right? So in that sense, there is no missing neighbor, right? Although it's finite, but you can find missing neighbors, right? So these two, boundary conditions, and out of this open boundary condition, there are several. In open boundary conditions, you can find, several other boundary conditions. Fixed boundary condition, variable boundary condition, right? Fixed means, as I've said, the missing neighbors, they are in some fixed boundary, fixed state. Variable means the state of the missing neighbors, missing cells, they may vary, right? That is the open boundary condition. So most popular is, out of several open boundary conditions, is null boundary condition. In case of null boundary condition, what do you assume? The missing neighbors are in state 0. 0 is a special state. Here if you consider, and the missing neighbors are in the special state. So these boundary conditions are assumed here, right? So in case of finite CS, we have to specify some boundary condition. Okay. Now come back to this asynchronous CA case, and we shall see, how the cells are updated in case of asynchronous CA. Let us take an example. So here we'll discuss about that one, synchronous updating as well as asynchronous updating, and here we consider rule 90. Right, rule 90 is considered here. Okay, we are considering here one-dimensional case. Okay, same thing, same style is applicable for other dimensions also. Okay, but to show the difference and the style of update, we consider the simple case, one-dimensional Cellular Automaton and binary Cellular Automaton, and we have considered here ECA, means a cell depends on left neighbor, self, and right neighbor, right? Okay. So here let us consider this one, 0, 1, 1, 0, 1, and this is my rule 90. And first we consider null boundary condition. Okay, let's see how we get the configurations. So what I have considered here, come back to this jam. Is my jam working? Yeah. So here the configuration I have considered is 0, 1, 1, 0, 1. And what C I have considered, that is rule 90. Right? Rule 90 I have considered. So this is first the synchronous case. Synchronous. Case. So synchronous case means, all the cells are updated simultaneously, and here my boundary condition is null. right? So what is the rule 90? I can get it from here. This is my rule 90. Should I write? Of why I'm not going to jam? Just a sec. Okay. And what is the rule here? So 0, 0, 0. Let me write it again. 0, 0, 0, 1. It is 0, 0, 0 is 0. 0, 0, 1 is 1. 0, 1, 0. I know it, so I'm writing. Is 1 again. And here 0, 1, 1. It is here. It is oh no. It will be 0. It will be 1. Then 1, 0, 0. This will be 1. 1, 0, 1. This will be 0. Then it is 1, 1, 0. It will be again 1 and 1, 1, 1. It will be 0. This rule 90. Okay, 0, 1. Yeah, it is rule 90. So I shall use this rule, right? Now here for the first cell, come to this first cell. Here in case of synchronous, my boundary condition is, what's the boundary condition? It is null. So here, sorry. Here, okay. So what I get here, in left hand side and right hand side, there are some 0 because I'm using null boundary condition. Now, so how it will work? So this is 0, 0, 0. Sorry, 0, 0, 1. 0, 0, 1 means it is 1, right? 1. Then it is 0, 1, 1. 0, 1, 1 is 1. It is 1. Then it is, so I'm getting 0, 1, 1. Then it is 1, 1, 0. For 1, 1, 0, I'm again getting 1. It is 1, 0, 1. 1, 0, 1 is 0. 1, 0, 1 is 0. And 0, 1, 0. So where is 0, 1, 0? 0, 1, 0 is this. 0, 1, 0 is 0. So 0, 1, 0 is 0. So this is my, so if this is my initial configuration, this is my next configuration. 1, 1, 1, 0, 0. If we further apply, then what will get? The similar way. Let us apply. So here again 0. In this case, I'm using null boundary condition. I have said I shall use null boundary condition. Then what I can get here? 0, 1, 1. 0, 1, 1 is 1. So here I shall get again 1. 1, 1, 1 is 0. 1, 1, 1 is 0. This 0. Then 1, 1, 1, 1, 0. This 1, 1, 0 is 1 here. So I'm getting 1. 1, 0, 0. 1, 0, 0 is 1. So we'll get 1 again. Right? And then 0, 0, 0. 0, 0, 0 is 0, 0. And so on. So now if I evolve this 5 cell rule 90 CA, then I'll get these configurations in this way. Then I can continue further. Right? This is a synchronous way. And note that what is the important implication of the boundary condition? Boundary condition has a great role here. For the left hand side, I have assumed always 0. The left hand side always it is 0. Right hand side always the cells, state is 0. That I've considered, and then I received the next configurations. So this is my synchronous CA. Now what will have the fully asynchronous CA? Fully asynchronous. Let's see. Here my condition was, I mean my initial configuration was 1 1 1 0 1, right? Now what is the fully asynchronous update? At at a time step, S cell is selected uniformly at random. Okay, so you have to choose one cell uniformly randomly. Suppose this cell is chosen for update. Okay, only you can choose only one cell, right? Suppose this cell is chosen, then what will happen? So you get 0 1 1. First of all, the rest cells, they will remain, they'll remain unchanged. Okay, but this cell is chosen, so 0 1 1. So what is 0 1 1? 0 1 1 is 1. Same thing. I mean, so this cell is updated only. Okay, this cell is updated, but the rest cell remains same. Although after updating I get the same one, that's a different issue. That depends on rule. I have considered this one, then I get again 1. I may get 0. That's a different issue. I may get 0 1, etc. But the point is here, this cell is only allowed to update state, and other cells, they have to remain, in their old state, right? Okay, so now you choose anyone, right? Say so next time step, suppose this is chosen, this cell is chosen. Okay, then what will happen? I am using null boundary condition. So here 0 is, there is a 0, so 0 0 1 I get, right? I get 0 0 1, come back here, 0 0 1, it is 1, so I write 1. So it's 1 1 1 0 1. So now here they say, I can write one more step. Say this, if I consider, so this one, suppose this cell is selected, right? So it is 0 1, here is 0, because null boundary condition. So the rest cell will remain same, 1 1 1 0, and 0 1 0 0 1 is 0 is 0, it will be 0 in this way, right? So therefore you can get this one. Okay, what I get here from this configuration, I move to this configuration, then I move to this configuration, then I move to this configuration, right? Now if you understand, if I get the different update scheme, suppose instead of this one, I can, if I choose this one or other one, I can get different next configuration, right? So from one configuration, I may move to different configurations based on the update one, right? Can I show this one? What I want to say here, suppose here you this 0 1 1 0 1, right? Okay, so here, so second cell is updated. Now suppose second this cell was chosen uniformly and randomly for the update. Suppose this cell is chosen for update. Suppose, then what you will have? then you'll have the next configuration is 0, 1, 1, 0, and this is 0, 1, 0, 0, 1, 0, 0, 0. So see, these two configurations, they are same. These two configurations, they are same. But right here, let me use different color. So these two configurations, they are same. They are same. But what I get here, these and these, they are not same. You can see it was 0, 1, 1, 0, 1. It is 0, 1, 1, 0, 0. They are not same. So therefore, my evolution depends not only on the rule, but also which cell is updated when. That property, I mean, that independence property tells you that in which configuration, additionally tells you that which configuration will go to what configuration. So configuration transition depends on here two factors. First, rule as usual. Second one, the which cells are updated when. In case of synchronous system, you can't get that one. You can never get that one. For this one, from this from this initial configuration, you'll always go to this configuration if boundary condition is null and your rule is 90. Right? There is a determinism. Right? There is a determinism. And reason is, where is the reason? All the cells are forced to get updated simultaneously. Okay, so this is a different synchronous and fully asynchronous operating scheme. Now let us discuss that one. This is fully asynchronous. Then come back to that one, the alpha synchronous, right? Things are not very difficult, but if you have any issue, please let me know. So it is called alpha asynchronous. It is again null boundary condition, right? Here, alpha means, alpha says the probability. Suppose here I have considered just any alpha I can assume here. Suppose alpha equal to 0.5. So I have considered alpha equal to 0.5. I mean, almost half number of cells will be updated. Suppose this cell not selected, this cell not selected, but say this cell is selected and this cell is selected for update, and this cell is not selected. Suppose these two cells, they are selected to update. Okay, alpha equal to 0.5 I have considered. Okay, so what does it mean? Let me repeat it again. Means a cell updates its state with priority alpha. Here alpha is uniform, right? Although some authors worked with non-uniform alpha, but here I'm considering alpha is uniform, and all the cells follow the same alpha. And following that one, suppose these two cells are selected for update. Okay, so firstly, they will remain unchanged. The state of this one, these three cells will remain unchanged. But here I have to consider these two cells. Okay, first 1, 1, 0. For 1, 1, 0, it's 1. It's okay. It's 1. And 1, 0, 1. For 1, 0, 1. It's okay. It's good. So I have selected two cells to update, and then these two are selected. But however, we get the same configuration. That may happen always. So after updating, I may repeatedly receive the same configurations. Okay, that may happen. Okay. So this is the configuration I get. Now suppose then this configuration and this cell is selected, and say this cell is selected, and say this cell is selected. Suppose 3 cells are selected for update. Then what will get? This is for 001. I'm using null boundary condition. Here it is 0 is there. To assume is 0 because it's null boundary condition. So 001, 1 is 1. It will be 1, right? 011 for this cell. If you consider 011, 011 is 1. Is 1. These two will remain unchanged, and here 010, 010 is 0. In this way, we update. So this is the alpha asynchronous update, right? This is alpha asynchronous update. Let me, if you have any question, you may ask at this stage. So here I have considered null boundary condition. I have considered null boundary condition, but I can do the same for periodic boundary condition. I shall give one example of periodic boundary condition, then I'll continue this part. So here for synchronous case, if it is periodic boundary condition, it will not be like this one. So now I am considering, say, periodic boundary condition. Periodic boundary condition means it forms a period, spatially it's periodic. Okay, that means different color. So I'm using this one. Okay, so let us see in case of synchronous case. In case of periodic boundary condition, it means that it forms like this one, circular array. Means after 1 you can get 0, right? So here what you get here, the first one, this first one, consider the first cell under periodic boundary. What has happened? Okay. This periodic boundary condition, first one is 1, 0, 1. So here, if I want to find out the next state of this cell, it is 1 in left hand side because its left neighbor is this one, first to last one. So I'll get 1, 0, 1. So it is 1, 0, 1. It is 2. Sorry, it is 1, 0, 1 is 0. I shall write 0 here. And 1, 0, 0, 1, 1 is as usual. The 0, 1, 1, it was 1, 1, 1, 0, it was 1, and 1, 0, 1, 0, 1, it was 0. But here 0, 1, here again 0, 0, 1, 0 is 0. So in case of periodic boundary condition, only this boundary cells the matter. Actually, it forms a circular array, and if a neighbor is right side of the rightmost cell, then first cell is considered. That is the idea here. It forms a circular array. So only, the boundary cells, their states matter. The rest cell remains same. However, if few cells are changed, whole configuration gets changed. So therefore, the dynamics, the behavior, what you see in case of null boundary condition, that behavior you cannot see in general for periodic boundary condition. So be it synchronous, be it asynchronous, if your automaton is finite, if your automaton is finite, then boundary condition has a great role. So here you can see that in case of rule 90, and in case of this, this initial configuration, it matters. So similarly, that is also true for alpha synchronous CA and full asynchronous CA. So all the cases, uh, I mean, it matters. The boundary condition matters. Okay, if you have no any question with this, then I can move to the next one. Okay, so this is about fully asynchronous update and alpha asynchronous update. Right. So we have seen, the uh, 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 the difference and the meaning of fully asynchronous update and alpha asynchronous update, and their role, and the role of boundary conditions during the evolution. Okay. See, one point is clear, that here cells are updated probabilistically, and as a result, we are getting different behavior. There are many works who claim that, this relaxation, in updating scheme is very natural. I argued that it is very natural, and this relaxation helps us modeling, uh, many natural phenomena. Okay, we shall not go much detail about asynchronous cell automata in this course. Just this introductory detail note. For modeling distributed systems, asynchronous cell automata was used, and as I've said, from natural phenomena also it is used. Let me state few important results before concluding this one. Let me state few important results of ACS, or asynchronous cellular automata. So just I'm stating the results. I shall not go to the proof. Say, important thing is very important result. Computational equivalence of synchronous and asynchronous cell automata. I mean, synchronous cell automata, they are proved as computational universal. Asynchronous cell automata are also proved as computational universal. In other words, they can, what does it mean? What does it mean? This, they can simulate universal Turing machine. Okay, so this line basically tells us that what synchronous CA can do, asynchronous CA can also do. Next result of the same author, actually, if you have D-state synchronous CA, then that CA can be simulated by 3 into D square state asynchronous CA, right? So very important result. The same paper, these two results are there. So D-state synchronous CA can be simulated by 3D square asynchronous, 3D square state actually, asynchronous CA with same neighborhood dependency. Okay, I am not extending the neighborhood dependency. I am not doing. I'm not, and the dimension is also same, right? So one thing you can see here, you are allowing independence among the cells. That has some cost. What task you can do with D-state system, D-state synchronous CA, for doing the same task, you need 3D square states. Okay, so in that sense, now you can argue that synchronous CA is better. At least this result is showing. State complexity is increasing here. Same task if you want to do, then you need 3D square state. Okay. Proofs are very simple. If you're interested, you can go to the proof. So this is, in some sense, cost of independence. However, lots of arguments are there. Although we have to bear more cost here, but that allows us more flexibility to model natural systems. Anyway, this is an interesting result. It's also very old result. Very old result. It says that D plus one dimensional asynchronous CA can simulate D-dimensional synchronous CA. If I increase one dimension, so one dimensional asynchronous CA is a very old result and it has written in different perspective. Okay, so if I increase the dimension, then D-dimensional cellular space, classical cellular space, can be simulated by D plus one dimensional asynchronous cellular space. So it also tells in the same line that you have to bear a cost to increase the dimension. It's also an interesting result. It's a recent result that 12. That fully asynchronous CA is very simple, simplest one. Fully asynchronous CA is the simplest one because only at one step, only one cell is allowed to update. Our simplest version of asynchronism. That simplest CA, that simplest asynchronous CA can also simulate universal Turing machine. It is 2012. It was proved. And it was also proved, also shown that asynchronous CA can also be reversible. What is the meaning of reversibility? The meaning of reversibility is you can go backward direction. No? We have discussed about reversibility in last few classes. A CA is reversible if it is bijective. Bijective means from one configuration you can go backward. So backward transition is possible, right? We call it time reversal. So evolution means from one configuration you're coming to the next configuration, so time is moving in forward direction, but here time is going as if time is moving to backward direction. So time reversal. That's the meaning of reversibility. We have received, we have studied this one. But as we have discussed, asynchronism in general, the opposite word of reversibility. You have seen in the example I have seen, from one configuration it can go two configurations, right? I gave that example. So from this idea we get how can I get this one-to-one mapping, right? How can I get this bijective mapping? So it can be bijective, right? But from different perspective of reversibility means if a system is finite, if you start from a particular configuration, after some time you'll come back to the old position, right? There's one meaning of that one. If we consider that meaning, then it was shown that even asynchronous CA can be reversible. So these are some important results. In this course, we have no scope of going into detail of this, you know, of uh, detailing of this result as possible. Okay, okay. So this is about asynchronous cellular automata, which we have got by relaxing synchronicity property, that is uniform update property of a classical cellular automata. Last remains the hybrid cellular automata, okay, where we directly question or disobey rather the uniformity constraint of a cellular automata, of a cellular automaton. Here, different cells may use different rules. In last case also, in asynchronous cellular automata, we have not allowed different rules for different cells. But in case of hybrid cellular automata, or they are popularly known as non-uniform cellular automata, they break this uniformity criteria. Okay, so different cells here may use different rules, right? So therefore, what you need to specify the rules of cells, right? You need to specify rules of cells, right? So you need this one, you need this set. In the classical definition of CA, we have a single rule, but here you have set of rules, right? So for each cell, you have to tell which particular rule the cell is following. That you have to tell here, right? So so you need this set. The set here I have written Ri. I belongs to this L. Right. Now, if it is one-dimensional CA, so it may be maybe any dimensional CA, but it's one-dimensional CA, right? Then what can happen? You can get a rule vector. You can get a vector, right? So you are placing one by one. For one cell, for the first cell, one rule, second cell, another rule, third cell, another rule. So you can get a vector, which is named as a rule vector, right? So like this one. So consider this a 4 cell say. I'm considering the each cell following these two rules, rule 90 and rule 150. See, as I've said, this rule 90 means, when I mention rule 90 means ECA rule 90, Wolfram's rule 90, or 150 means Wolfram's rule 150. Now, suppose 4 cells 90, 150, they are using this one. First cell using 50, 150, second cell 90, then third cell 150, then fourth cell 90. If I add them, I can get a vector, right? I can get a sequence, a rule sequence, which is popularly named as rule vector, and this is for one-dimensional CA. Although hybrid cell automata or non-uniform cell automata, they are defined for any dimension, almost all works concentrate on one-dimensional case, right? So when you talk about hybrid CA, then we generally specify rule vector, right? Or if I specify field rule vector, it means we are using hybrid cellular automata. So this is an example, okay? And hybrid cellular automata we will discuss in detail. Okay, in my course, we discuss in much detail of this hybrid cellular automata. Next class we shall continue from the hybrid cellular automata. So I'm just telling you the basics of this hybrid cellular automata. So suppose as a 4 cell C I have taken. So the rule vector given, and this is the say 2 rules. And just I'm telling you how they act. Suppose they are the cells. So 4 cells are here. You can see the 4 cells marked as green, not as green. So we loaded. We have loaded the CA with initial configuration. Suppose initial configuration is 0001. And here we are using null boundary condition. And the next 2 step, see have it in a clock means I'm using synchronous. This is asynchronous, right? So it is not asynchronous, it is synchronous, right? So when a clock is coming, then all cells are updated. I get the next configuration. Then again, if clock comes, all cells are updated. I get the next configuration. And see here, you can see here that how it is calculated. When I use this one, when I find out, so let me go back to that one. See, when I use for the row cell 0, when I want to get the next state for the cell 0, what I get 0, 0, 0, and the rule what I use 150, not 90. Why? Because first cell is using rule 150, so I'm getting 0. I'm getting 0 here. For the next one 0, 0, 0. Here it is 90, right? Rule 90. So I have to consider 90 here, not rule 150. So I using run print, I get 0. I know this, so you can see, you can check it from the table also. You can check it from table. 0, 0, okay. Now here 0, 0, 1 for third cell. I think you can see my mouse. So I'm not writing, I'm not using Jamboard anymore. So so here 0, 0, 1. Okay. So it is rule 150. Come back here in this table. 0, 0, 1. 0, 0, 1 is 1. Is 1 is written here. For the fourth cell, 0, 1, 0. It is rule 90. It's rule 90. 0, 1, 0, rule 90. Right? I'm getting here rule 90. So in this way, so therefore, when I update a cell, then I have to consider which rule that particular cell is using. Classically, we need not to look at any particular rule because all the cells are using the same rule. But here we have to consider the rule on which the cell is working. Right? In this way, I can get the configurations. So it is for null boundary condition. As I've said, for periodic boundary condition, this is the case will be different. I mean, configurations will be different, etc. So this is here. In case of hybrid cell automata, the uniformity constraint is disobeyed. So different cells may follow different rules. In last 3 or 4 decades, especially after late 80s, cellular automata have been used actually in the domain of technology. Have been used as technology. Okay, so for example, cryptography, random number generator, VLSI circuit testing. In several cases, cellular automata have been used, and for all the cases, this hybrid cellular automata they are used. right? And in for almost all cases, the automaton is considered as binary, means each cell can be in any two states. Each cell can be in two states, 0 or 1. And again, almost all cases, the cells follow Wolfram rules, like 90, like 30, like 150, etc. If you go to the literature, most of the works on hybrid cell automata, better to say almost all works, they consider these kind of rules, Wolfram rules only. Okay, so in coming class also, I shall consider this CA named as non-uniform cell automata in detail. Non-uniform cell automata or hybrid cell automata, both the names are used in detail, where the cells will use the Wolfram rules only. So anyway, to sum up, we have started with three uniformity constraint of cellular automata, cellular automata, and we relaxed all the constraints. By relaxing uniform neighborhood constraint, we get automata network. By relaxing the uniform update or synchronicity, we get asynchronous cell automata. By updating, by dissolving the uniformity constraint or uniform rule constraint, we get hybrid cell automata or non-uniform cellular automata. So these are the main variant of non-classical cell automata. However, these are not the end. There are other variants that we are discussing here. Okay, so these are the three basic variants of non-classical cellular automata. Okay, that's all for today.